a bit hard. So few of them are a bit hard. So obviously we may not be able to do all of them, but yeah. So mm, which one do we start with? Do we start with an easy one, or let's do okay? Let's do a relatively okay. Let's do a medium one. Um, find all pairs of positive integers, comma, and such that uh, this thing. So a minus 1, a squared minus 1, dot, 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 a to the power n minus 1 is equal to, is a perfect square, so equal to t squared. Yes. Okay, I'll give you a little bit of time. This is a good problem. Like, you should try it a bit. It's a bit tricky, but it's also quite instructive.
Is it t square?
Yes, it is t squared. Find all positive integers a comma n such that this thing is a perfect square.
Okay.
Also, if anybody has done this problem, shall I give you another one?
Yes.
Okay. Okay, let me look for another one. Hmm. Um, let a1 dot 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 an be distinct. Oh, is my camera switched off? Oh, I forgot to switch it on. Stop it. Yeah. Yes. Let a1 dot dot an be distinct integers. Show that this product equal to I plus then j plus n equal to n of ai minus aj I minus j is an integer. Yes. Okay, so whoever has done the first one can try the second one. We will get to the second one as well. Don't worry. What did I miss? Oh, nothing. I just wrote down the problem. Try the first one if you haven't seen it. And if you have seen it, you can try the second.
Could you scroll a bit towards the right so that we can see the second problem? Yeah. Yeah.
Anyways, if you have any idea, even if it feels unrelated, you can ask. The best way to learn is to realize why ideas work and why some ideas don't work. So yeah, if you have anything, you can just unmute and share it with us. So, any ideas? Okay, anything like what do you think? What approach do we follow? What do you think like would be used in this problem? I'll just wait for maybe 2 or 3 minutes, then I'll spoil.
So we can factor out a minus 1 first.
Yes?
Yeah, we can factor out a minus 1 from all the terms.
Okay, sure. That's a good idea. We write it as a minus 1. There are n terms, so it will be raised to the power n. So okay, we have 1, a plus 1, and the second term is a squared a plus 1. And then we have a cube plus 1, and then yeah, it goes on. We want this thing to be a perfect square. Hmm. Okay, so you might think about splitting it into two cases because we have n here. Um, if n is odd, then if n is even, then this term is already a perfect square, so we can focus on this term. And if n is odd, then you can just like remove all. If n is like 2k plus 1, then you can just remove the 2k, and we have just a minus 1 into this thing. And you have to show that you have to do something with it.
We can also try
Yes.
the degree of any time divided by maximum.
Sorry, I couldn't hear you. Can you say that again?
Can we find some prime whose order is only one time existent 1 to n?
That's a good idea. So, okay, I'll just write it a bit. Idea: find prime such that order comes the multiple of order rather comes only once in 1 to n. And order. Nice. That's a step in the right direction. How do we find such a prime? Well, rather, um, controlling the prime divisor. Well, controlling like the order of A mod P, like if you want to vary P, that would be hard. Should be better to like vary N. So what you do, you take some N, like you decide what K you want, and you look at the prime divisor of A to the K minus 1, and then you do something with it. That's um that's a more viable strategy. The question is what do you pick? Like, what K do you pick from 1 to N? Also, do you have any guesses for the answer? Like, it would be helpful to have something in mind to try and prove it, right? So if we have n equal to 1, equal to 1 is like obvious. N equal to 2 gives us a minus 1 into a squared minus 1. And like, yeah, you can factor, this part is always a square, and you can always make this a perfect square. So yeah, n equal to 1 and 2 have solution. Okay, wait, I did forget to mention one thing. A, okay, wait. A is even, by the way. Keep that in. All right. So it's 5 o'clock. Yeah, I will. Let's elaborate on this idea. Um, you want to pick a k from 1 to n. You want to pick a k such that if we have some prime p dividing a to the k minus 1, then the order of p is good. Order of a mod p is good. Something that you can control. How do you do that? The first idea, the first thought is to let this thing be a prime. Let this be q. Right. So in that case, you get if like a to the q is congruent to 1 mod p, then the order of a mod p is either q or it's just 1, right? A is equal to 1 or q. Yeah, so now what? Well, how do you remove this one wala condition?
Access to an A is equal to 1 by.
No, wait, order of, yeah, okay, sure, that also works. But what if it means that a is congruent to 1 mod p, but what if p does divide a minus 1? Yeah, so the idea is instead of looking at a to the q minus 1 alone, you look at this thing. Like what you do, you have a minus 1 times like a squared minus 1. You do this, you'll arrive at this term, and you write it as this thing, and you club these two terms together. So you have a minus 1, the whole squared, into some random stuff, into a to the power q minus 1 upon a minus 1, and then some more things. And this is the okay, this is a perfect square, you don't need to consider that. But now you take a prime divisor of this thing, consider a prime divisor of this thing, and then if you notice, then p does not divide any other term, right? Because then p divides a to the q minus 1, the order is 1, but like we are already ignoring this term. So sure, this is fine. Now what? Now, what you want to do is you want like, okay, a divides q, p divides a to the q minus 1, but p also divides a to the 2q minus 1. So what you want is that 2q should not lie in this range, like should not be from 1 to n. How do you deal with that? What you do is you make q less than n, well, less than equal to n, and 2q greater than n. So what that means is that and we know that this thing, like a prime in this range from n by 2 to n, we know that it exists because Bertrand's postulate, right? We know that it exists. So essentially, what we have just found is that if we take any prime divisor of this thing, then it does not divide any other term, and further, like it just does not divide any other term. So this thing has to be a perfect square. It's co-prime with everything else, right? It has to be a perfect square. So we get a to the q minus 1 upon a minus 1 is equal to L squared, right? The issue is, how do you deal with this now? Because uh, this is not easy. In fact, this was proved quite recently, that like 3 comma 5 and like 7 comma 4 comma 7 and something 7 comma 4, like they are the only solutions. So yeah, you do not want to go this way, because you this is not a well-known theorem. Like, yeah, the proof exists. This is a like theorem. This has been proved, but you cannot state it in olympiads, nor can you solve it on your own. Like, you just can't. It's too hard. So this approach, the thing we tried, is not gonna work. Okay, so what do we do? Any other ideas?
We could try using LT and just find a few contradictions or something, because the VP has to be even.
You want to use LT?
Yes.
Okay, sure. How do you use LT here? Let's see. That's also a good idea. I'll just write it down somewhere here. Um, Idea number 2. LT. Right. Okay. This in fact LT should be idea number 1. But yeah, like fine. If you haven't done LT, orders is the most natural thing.
I did say it, but I don't think you heard it.
Oh, okay. Well, yeah. How do we proceed using LT? Shall I? Okay. Let's see what you could do in LT. Suppose you take a prime. Um, Prime dividing a minus 1. Do we want a in? Okay, let's do prime dividing a minus 1. Then VP of a to the I minus 1, like odd prime. Forget 2. Or this thing is equal to VP of a minus 1 plus VP of I, right? And then you want to sum of a to the I minus 1 is equal to the summation of VP of a minus 1 plus VP of I, right? As I goes from 1 to n. And this thing is equal to, you take the VP of A minus 1 outside because it's constant. N VP of A minus 1 plus I equal to 1 to N, the VP of I, right? And this term is VP of N factorial. Do you see why? You just like, because VP is multiplicative, right? Like not VP of A plus VP of B is equal to VP of AB. So yeah, this is VP of N factorial, and VP of N factorial, we know that it's N minus SP of N upon P minus 1, and SP of N is the sum of digits of N in base P. And we had N VP of P minus 1. This is what we have now. How do you proceed from here? That's the question, because getting a control over SP of N is a bit hard. Especially you have P minus 1 in the denominator, right? How do you find whether this thing is even? And how do you deal with this? Okay, you could make N even, but then this part is a bit trickier to deal with. What you could do is like here maybe you assume something else. P divides A to the something else minus 1. But yeah, I mean, okay, you should actually explore all that. But we do not have infinite time, so like there are better questions to get to. So I'll just tell you, at least the solution I have in mind does not use LT. You can always explore on your own and find something else, but yeah. Okay, so shall I spoil the problem now?
Sure, I should say it's been enough time.
Okay, fine. Then I will spoil the problem now. The idea, okay, idea number 1 was actually correct. Like you want to find some P and some N such that the order is like order comes only once. So the idea is to consider the power of 2 to k minus 1 and less than 2 to the k. You do this and you look at a prime dividing a to the 2k, a to the 2 to the k minus 1. Why do you do that? Because you can factor it. K minus 1 minus 1, a to the 2 to the k minus 1 plus 1. And now what you can do, if you just take a prime divisor of only this part. So in fact, like forget this, change the condition and take a prime divisor of this part, then we can fix its order. Because like if a to the 2 to the k minus 1 is congruent to minus 1 mod q, then I think it has already been done, but like okay, I'll just do it again. A to the 2 to the k is congruent to 1 mod q. So the order of A mod q divides 2 to the k, but it cannot divide 2 to the k minus 1 because this is a minus 1, not a plus 1. So you get that the order of this thing is exactly equal to 2 to the k, right? And now you have like an equality in orders, and I just want to emphasize this is a very common idea. You look at powers of 2 in the exponent because their orders are good. You should always have that in the back of your mind. So again, we have an order. We have fixed the order. And now look at this. We know that 2 to the k, like n is... Okay, actually change the bounds here. Make it something like this. Yeah. We know that n is at most... wait. Yeah, n is like we have order is equal to 2 to the k, right? And like the order is greater. Okay, wait. Okay. Uh, Consider this. So this thing becomes a minus 2, 2. One. Yeah, so order is like 2 to the k minus 1. And we know that 2 to the k minus 1 is like less than n, is less than equal to n, but like 2 to the k is like more than n. This is what we know. So the order comes only once from 1 to n. Like we have 2 to the k minus 1 here, and after this you have 2 to the k. So we get that if we consider a prime divisor q of 2 to the k minus 2 plus 1, you will get that it divides only one of the terms. In fact, this thing, it divides only one of the terms, and it also divides this thing, right? So it means that it has to be a perfect square, right? Wait,
Yeah.
this has to be a perfect square. So make it equal to like L squared. And this should ring a bell because powers, we have perfect powers on both sides, and we know Catalan's conjecture, right? So the only thing satisfying here is like uh, k minus, if we have 2q plus 1 is equal to 3 squared. And yeah, this is like, from this you can just eliminate basically most of the n. But yeah, I'll just mention this. This works only when k is greater than equal to 2, right? So for k is less than 2, that is for n equal to 1 to 3, you have to verify that solutions don't exist. We know that solutions exist here. We have to prove that no solution can exist here. And I'll just leave this as an exercise for you all to do, because I want to move on to other problems. But yeah, it's not very hard. Also, if you are unable to do it, then you could just message me. I can help you. But yeah, this is a very crucial idea. Like, the solution seems short, but it's tricky to think. So yeah, let's move on to another problem. Mm, uh, yes. Find.
How do you solve the k equals to 5 case?
You don't need to solve k equal to 5 case, right? Like, oh, acha, you mean here? Okay. For when you put in k equal to 5, then you get like k is equal to 5. Then if you look here, then n is like between 4 and like less than what, 2 to the 5. Yeah, so it's from 16 to 32. And yeah, you are going to die there. But I mean, you have this thing, right? So L is equal to 3.
Right,
So
I don't see why n is k equal to 5 should be a special case if we're only looking at ones less than or equal to 3.
uh no, like, because this thing has a solution for k is equal to 5. That's why he's pointing it out.
Oh, I see. All right.
Like, that's the only solution for Catalans, right?
Yeah,
Yeah, so that's why we need to take care of this.
sure.
For k is equal to 5, we have like a large range of n, but okay, hold on. Oh, wait. For k is equal to 5, you can fix the value of a. Okay, wait, just a second. Okay, here we are taking odd prime. I forgot to mention this. And we can do that because then the odd prime does not divide this part, right? It divides only this thing. because like it's not 2, so if it divides this, it cannot divide consecutive odd numbers. And as for the k is equal to 5, um, okay, just a second.
By the way, shouldn't the a to the power 2 to the power k minus 1 plus 1, that should be a perfect square, like minus 1, like why is the other thing perfect square? Actually didn't get you on that.
Wait, which part are you talking about?
Like we get the there exist a prime such that a to the power 2 to the power k minus 1 minus 1, the
Mhm.
VP of that is odd,
Yeah,
and
sure.
that prime doesn't divide any of the previous things.
Oh,
So
wait,
this is not.
wait. Okay, yeah, we are looking at this. We get a prime which we get an odd prime which divides this, but it does not divide this, and it does not divide any other term.
So we just want a to the power 2 to the power k minus 1 minus 1. That part to be like a perfect square, like
No, we are not looking at that. We use this, and then we k factorized here, and then we shifted our focus to this. So wait, I'll just write it here. We have like the term, like the big expression is like, I'll just write E for short. E is equal to some other E dash into a to the power 2 to the power k minus 2 plus 1, and these two things are co-prime. So you get that this thing is a perfect square.
so yeah, that is fine. Like
Yes.
what I'm trying to say is, by the way, you assume 2 to the power k is less than equal to n, or 2 to the power k minus 1 is less than equal to n. Okay, yes. So
Yeah.
no, when you are doing this, p divides a to the power 2 to the power k minus 1 minus 1. So
Yes.
wait one sec.
Uh,
Yes.
like
So
okay,
the prime,
hmm,
the prime that divides like a to the power 2 to the power k minus 2 minus 1.
yes. Oh,
Uh,
okay. We are taking an odd prime which divides this thing, right? Like that's what we are
yeah, the
taking.
first thing. Yeah,
So
that's
it cannot divide the second thing.
yes, it cannot divide the second thing, and we want to show, and it can't divide any of the things that like came before, right?
Any of the things that came before or comes after.
So basically, we want to show a prime exists as that VP of this is odd. Or
Yeah.
if we try to do that.
Yeah, we are. And for most of the things, it is not. Like from Catalans.
Yeah, now I'm trying to say that like is a to the power 2 to the power k minus 1, like not only the power, right?
Here are you talking about? I see. Okay, I see. I'll just, how do I, yeah, okay. A to the power 2 to the power k minus 2 plus 1 is equal to L squared. Is this what you're talking about? And then here you apply Catalans.
I mean, we can do it minus 1, yeah, plus 1 also, yes.
See, minus 1 does
Here we
not have
apply
a,
Catalans.
minus
Yeah,
1 does
not
not have a
minus 1, I
constant.
mean plus 1, yes.
Using Catalan and NT is just sad.
Because
Can't
there
we
is a
not?
prime such that,
Yeah. Okay, why is
I mean,
using
here we
Catalan
can
and NT
also use
sad?
orders such that.
Oh yeah, here we can just like we can do a lot of stuff. Like we can factor. Um, I mean, ideally,
Wait, we
like if
don't need to factor. By the same like ordered thing, we can say that like there exists a prime such that it does not divide any of the things before, and after that just use Catalan to do that.
okay, hold on, just a second. In fact, whoever is this, what is Catalan? Okay, if you don't know Catalan, okay, why am I doing this? If k is greater than equal to 3, then this thing is a perfect square. And this thing was also a perfect square. And the difference between two perfect squares cannot be 1. Like one of them has to be 0. So that's a contradiction. Does that make sense? You don't even need Catalans for this. Is that all right? And yeah, like again, k equal to 1 comma 2. So like for um k less, okay, actually, yeah, for n equal to 4 and 3, you will have to check for yourself. 4, yeah, 4 should be fine. 3 is a bit tricky. 1 and 2 obviously have solutions. I'm just leaving that for you to do. So yeah, shall I move on? Any other doubts?
I think someone asked what's Catalan.
Oh yeah, we did not use Catalan in the end.
Right.
Okay, then we will move on. Okay. I'll just write it here. Um, find all pairs of positive, okay, all pairs a comma b in positive integers such that a plus 1 divides b squared plus 1 and b plus 1 divides a squared plus 1. This is a good question. Okay. Okay, if you have done this question, you can try this one. This is Lagrange interpolation. Oh, wait, which one? Are you talking about this one? Oh, is it? Even if it is solve this without that. Maybe Christmas theorem helps. Are you talking about this one? Sure, you can think about Christmas theorem. Um, the issue is that you have not like Christmas theorem isn't very strong condition, right? It's like the primes are of the form 4k plus 1 and the ones with even VP can be 4k plus 3. And the condition on this does not really relate onto this that well. So you can try Christmas theorem. You should try any and every ideas you have, but it might not be helpful. Okay, it's like 5:30 almost already. How long extra can I take? Like the class started a bit late, so we are like if after doing this, I wanted to do the hard one, but we have little time left, and like it's a good problem. I cannot rush it.
What if we begin the hard one now? Would that still take enough time?
Um, yes.
Right, then we could do that one. We can complete it by that time. I think we can end 15 minutes afterwards also because we started 15 minutes late.
Yeah, that I was thinking about that. Wait, what was the question in it? That is a statement, not even a question. Oh, show that this thing is a in an integer. Yeah, like, write it, prove that. Same thing.
By the way, is A1 to AN like an infinite sequence and that holds for all n?
Oh, no, no,
Or
no.
n is a fixed integer?
No, for any n comma AI, like for any n and sequence AI.
So this is the infinite sequence.
No, like you take any n, like you take n equal to 5, you give any 5 distinct integers, and this thing has to hold true. Anyways, I'll start with this one. So, whenever you have such divisibility conditions, two things which are symmetric, the idea is to look at this and make it the same. Right, that's the idea. And you see, like, if you look at one of the terms, we have a plus 1 divides b squared plus 1. You have a square with b. So you want a plus 1 divides something with the square of a, and then you add, and hopefully it becomes. Yes, that's right. You know that a plus 1 divides a squared minus 1. So if we add, you get that a plus 1 divides a squared plus b squared. And similarly, b plus 1 also divides a squared plus b squared. Right.
Right.
Why?
So both of them divide a square plus b square.
Exactly. So you get that their LCM also divides a squared plus b squared. B plus 1 squared plus b squared. Now what? I feel like GCD is always better than LCM. So whenever I see LCM, I just rewrite it in terms of the GCD. So LCM of a comma b is LCM of x comma y is just like xy upon GCD of xy. So you can write it. Now what? You obviously want to remove this GCD condition. Like you want to prove that a plus 1 and b plus 1 are maybe co-prime, or maybe they have like small GCDs. How do you do that?
Their GCD must be 2 or 1.
That's right. Because if you consider a prime dividing the GCD, then like p divides a plus 1, p also divides b plus 1, and t divides obviously a squared plus b squared. So you get that a squared, like a is congruent to minus 1. So I'll just write that a is minus 1, b is minus 1. So you get that a squared plus b squared is congruent to 2 mod p. And we know that p divides a squared plus b squared. So p divides 2. So p is equal to 2, or like just co-prime. Right. So either this thing is 2, this thing is 2, or it's 1. Now what? We obviously, like, this is like, when you have something like this, you know that it's good progress. Faulty argument. Why so? GCD can be 2 to the k. Okay, but replace like p. Okay, p is not a prime. We didn't use the fact that p is prime anyway. Yeah, so then the GCD is either 2 or 1. Okay, yeah. So a plus 1 times, wait, I was okay. B, yeah, b plus 1, either this thing divides. Right. So you can see that in both cases, a plus 1 into b plus 1 by 2 divides a squared plus b squared. Like, ideally, you should not do this. Like, if you have two different cases, deal with them separately. But the point is that, uh, like, you have to solve this case either way, right? So if you solve this one first, like, it seems to be the tougher case. Like, obviously, actually, this one is the easier case. My bad. Like, you solve the easier case first. Right. So what do? You can rearrange. Right. What now? I'll just give you maybe a few minutes to think. By the way, if I'm going a bit fast or anything, you can feel free to interrupt me. Like, obviously, we don't have much time and I want to do good problems. So there's going to be losses somewhere. So we will probably just not do this problem. Like, we'll just do this one. This is a nice problem. We have to do this. I'll be right back in just. Add a 2 into a plus 1 plus b plus 1 to the RHS. That probably helps. Oh, okay. Let's see. We know that a plus 1 times b plus 1 divides. Right. So, yeah, it should be 4 into a plus 1. If you add this, you have 2a square plus you have like 4ab plus 4a plus 4b plus 1. You have 2a square plus 4a, and you can just make it 2 into a plus 1 the whole squared plus 2 into b plus 1 the whole squared plus yeah, so you had a 4, you used a 2 here and you used 2 here, so you have to do a plus 2. You used a and b terms, you didn't use ab, so you have plus 4ab. Okay, now what? I mean, maybe you could think about replacing a plus 1 with x and b plus 1 with y. It would be a bit better, like x squared plus y squared. And this thing, however, would become a bit bad. Right. It also creates an a plus b the whole squared term. Yeah, you mean like a 4ab term? Yes, it does. No, if you use 2 instead of 4. Oh, acha, do you want to use 2? Oh, okay, let's just add 2. You are adding 2ab plus 2a plus 2b. Oh, acha, you want to use like a plus b the whole squared and oh, okay, okay, plus 2. So this thing becomes a plus b the whole squared, a plus a squared plus b squared. Just like you have a 2a plus 2b plus 1 plus 2. Ah, this is actually not very bad. This is like not bad. This is a good idea. Good. Is that correct? Let me just. Hmm, yes, that's correct. Hmm. The issue is how do you deal with this from here? Like, okay, if you write a plus 1 equal to x and b plus 1 equal to y, then you have like, okay, just a second. Yes. If you have a plus 1 equal to x and b plus 1 equal to y, then you have like xy divides x squared plus y squared plus x plus y whole squared. Rather x minus x plus y minus. Still, like, now what? You can obviously try this approach, but intuitively, like whatever you do, it will not be reduced. Like, you can manipulate as much as you want, but like this is the best, like this is the simplest thing to deal with. But yeah, you can try it on your own.
So putting xy, you will get a term for minus 4xy which you can remove. So you'll have xy divides 2x square plus 2y square minus 4x minus 4y minus 2.
Uh,
In this one,
yeah,
the one
wait,
which I was
are you talking in this one or the 4AB wala thing?
4ab one.
Oh, acha, okay. 2x squared plus 2y squared plus 2. Yeah.
Minus 2, I think. Am I wrong? Hmm? Yeah, I think it's minus 2.
Um, Wait, how does this term get vanished? Like, you're putting x equal to a plus 1, right? So a is equal to x minus 1. And you have some x terms and y terms as well.
Hmm. So this term does not get vanished. When you multiply it out, you get a 4xy, right? When you expand it, that vanishes.
Oh, acha, that, yeah, that will vanish. Still, yeah, like, okay, like, I really want to spend more time and like listen to other approaches, but we do not have that much time. We don't have that much luxury. So I'll just move on. I'll just tell you the idea right now. We have a plus 1 divides 2a squared plus 2b squared. So you get like 2a squared plus 2b squared is some t times like a plus 1 times b plus 1, right? And now you use Vieta. And it may seem a bit random, but it's this a squared wala term which sort of motivates it. Because like whenever you have only a squared terms and you have some linears, it's always a good idea to try Vieta. It's a very magical concept. It's a very nice concept. So yeah, just write it in terms of A. I'll just take it in terms of A, like A and B are symmetric, so it doesn't matter. Plus, yeah, this is like TA into TB. You send like, okay, I'll just expand TAB plus A B plus T. Yeah, and then you get 2A squared plus you combine these, you send it on the other side. You'll get like A minus A times T plus 2b squared minus tb minus 2. And now you suppose like, okay, like this is a quadratic equation, there will be two roots. And if you consider the, okay, I have this tool. If you consider like this quadratic equation, it has two roots. One root is just like a. So suppose the other root is alpha, right? So now you have to be a bit careful. This is where like if this was in a contest, this is where you might lose marks. The idea of Veta jumping is to ensure integer roots. We cannot directly ensure integer roots because we have a 2 in the leading coefficient. So alpha plus a would become like tb plus t by 2. We need to ensure this is an integer. We can't just state the integer and it works. So how do you do that? This is where you want to split into two cases. Wait, where did I? Yeah, this GCD is 2 or 1, right? So suppose we are dealing with the case where GCD is 2. That means both a plus 1 and b plus 1 are even. Even, right? Okay, so you use this thing here. This is like t into b plus 1 by 2, and it's an integer because the numerator is even. Nice, we have to mention this. Like, I mean, like, you probably saw what happened in RMOP5, like, not writing acute, like, lost to maybe 5-7 marks. You have to be careful about this stuff. Like, if this was in a contest, you would have to specifically mention why it's even. You can't just say it's even. Yeah. So it's like this belongs to an integer. And a alpha is equal to, yeah, 2b squared minus tb minus t upon 2. And you see that this is even, and this thing is the same as this numerator, and it's also even. So this also belongs to integer. Hence, our alpha is an integer. Nice. What now? Now, the point is that in Vieta jumping, what you do is suppose that either A is greater than B or A is less than B. We haven't done that yet. And in fact, we will decide what to do. Like, we will manipulate the expression a bit and then we will see. So notice that this thing is less than like 2b squared by 2, and this thing is just b squared. So we have A alpha is less than b squared. So alpha is less than b squared by A. And what we want for the Vieta jumping is to show that alpha is less than A. Right. So that way you have two roots and you can always go to the lower root, and you get a infinite descent contradiction, right? So what we want this thing to be less than b squared by A. Right. Then the thing would hold. That is, we want A squared less than b squared. So we want to take A less than b. So this is what we select. This is correct, and this one is like we ignore this. So, and like, yeah, this is how you get the contradiction. So what if the GCD wasn't 2? We are done with this case. What if they were coprime? Well, then, like, you don't have a 2 in the, like, here and here you don't have a 2 to begin with. So you are good. Then in the equation, this two would become a 1. Yeah, this 2 would become a 1. So, like, you would automatically have A alpha is less than, like, you would automatically have that alpha as an integer. Further, you will get like b squared minus uh tb minus t less than b squared, and you suppose the same thing, and it's again a contradiction, right? And that is why we are done. So yeah, when you write this up in a contest, you have to, like, this is your rough work. You figure out that you will use A less than B, and then when you write it up, you write that in the beginning, like, as if you just happen to know. Similarly, in this problem, if you were to, like, we first considered P dividing this thing, and then we looked at Q dividing this thing, right? So while we write up, we just ignore this case. Like, we just write what's necessary. Now, it's 5:48. I'll be taking till 6:15, so we can, I think, we do have enough time to try this problem.
This is a crazy solution.
Yeah, this one is a great solution.
Yeah.
Find all primes such that, yeah, this one is such that Find all primes p such that p to the p plus 1 plus p plus 1 whole to the power p is a perfect square. Yeah, try this problem. This is a good problem. This is also a very instructive problem. Has anybody seen this problem? Okay, nice. Then try this.
I don't
Yeah,
think so.
perfect.
Yeah.
By the way, the problem I shared at the start, is anybody done with it?
The
Uh,
buffer? No.
this one, has anybody done this? Oh, acha. Okay. Sure. Anybody else?
Not finished with it. No.
All right. You can try this after the class.
Yeah.
And yeah, if you're stuck, you can just ask me for help. By the way, that problem is in AMN. So
Sorry, what?
the source of the buffer problem is AMM, American Math Monthly.
Right. All right.
I'll give you um I'll give you till maybe 2 more minutes before I give a hint. Right.
Sure. Just a little bit after looking, my guess is I don't think there exists such a prime.
That is right. There is no such prime. Like 2, 3, 5 don't work, yeah. Checking
Yeah.
for 7 is not feasible,
No.
but yeah, there is no other prime. Okay, so first thoughts. We have p to the p plus 1 p plus 1 to the p equal to say t squared. So what do? We have a square on the RHS. The idea is that that's sad. There is no solution. Yeah, that's kind of sad, but
I mean, you could just factorize it by taking p plus 1 to the right.
yeah, you want to take this. Oh, yeah, you want to take this to the right because then uh, if p is greater than equal to 2, if p is greater than 2, then this thing is even and this thing a perfect square. So you take it to
Yeah.
the right and you can factor, which is like a very common idea, right? It's the first idea
Right.
of the
So
lesson.
p plus 1 to the p is equal to,
Yeah, and that is also good. This is a perfect power.
right. So n minus, um, okay, fine. So it'll be, yeah, t minus p to the p plus 1 over
And
2.
now we can moreover notice that t is prime to p, so that brackets
Ah,
to be
ah,
prime.
they are not co-prime to it.
No,
Like,
no, it's
yeah,
actually GCD2, sorry.
yeah, they are GCDs too. You have to take care of that.
Yeah, GCD2. So
Yeah, exactly. So, like, I'll just write it down. If D divides both of them, then D also divides 2 to the power 2 times P to the power P plus 1 by 2.
Yeah.
And then the point is that and D divides T as well, right? But
Yeah.
D cannot divide this thing because if you note here, T like P does not divide T. So that
Right.
if D divides this thing,
wait, it's d divide 2t, right? Not d divide.
yeah, D divides 2. Like D cannot divide P, the P wala part, because
No,
that
in the
would be,
below thing you wrote b d divides t. It should be d divides 2t.
oh yeah, sure. It's D divides 2T. Like
Sure.
if D divides this P wala part, then D cannot divide 2, so D divides T. And then P divides T is a contradiction from our original statement. So that implies that D divides 2. So the GCD is like GCD is 1 or 2. In fact,
Like
blah,
since p is
blah.
odd, so t is odd, and
Yeah, exactly. T is odd and P is odd. So 2 does divide both of the things. So GCD is, in fact, like 1 is rejected. GCD is 2, which is sort of sad because you want to be able to directly just make them co-prime, but yeah, you can factor them out. Further, note that if you look at the V2 of this guy and this guy, then one of them has to be 1.
Right. Yeah.
Because like if 4 divides this thing and 4 divides this thing, then 4 has to divide this thing. That means 2 has to divide this thing. And we are working with an odd prime, so that cannot work.
so yeah, just like one is 2 into something
And yeah,
perfect
one
power
is 2
p,
into an odd thing, and the other is 2 to the something into an odd thing. Right.
and those odd things are both are perfect power p.
Yeah, the odd things are perfect powers.
So
So
now we can work with two cases, or
yeah, we will split into 2 cases. So but now look at this, like the V2 of the LHS is equal to P V2 of P plus 1.
Yeah, so
So the V2 of the RHS also has to be the same.
right.
So like if V2 of one of them is 1, then the other one has to have V2 this thing minus 1.
So PB2 of P.
Yeah.
Yeah.
So yeah, this is as Ronet said, we are going to split into cases. Case 1, V2 of the first thing. What was the first thing? The negative one.
P to P.
This one by 2,
Uh,
1.
okay. Yeah. Yeah.
This is the first case we are dealing with. So then the V2 of the plus wala thing is going to be the thing I just mentioned,
Yeah.
equal to of P plus 1 minus 1. Right. So just write this into like the first factor is just 2 into A, and the second factor is like 2 into 2 to the power P V2 of P plus 1 minus 1 into B. And further, as somebody pointed out, they have to be perfect squares because the product of, like, if you take out the 2 wala factor, this is a perfect pth power, right? So the product of two coprime things is a pth power, so each of them is a pth power. So write this as like to the power p and to the power p. Further, you have mn is equal to p plus 1 upon the v2, 2 to the power 2 to the v2. Right. Does that make sense?
Just a minute. So you put A as M to the A and B are perfect powers.
Yes.
So you're multiplying.
Yeah, because mn is equal to mn whole to the power p.
Uh-huh. So you can remove. Yes. Okay, I see. Fine. 2 VP.
Yeah. Okay, so I'll wait for some time, let this sink in, and if this part is clear, try to push this further. But t isn't odd, is it? Oh yeah, wait, t has to be odd, right? Because p plus 1 is even, p is odd, so t has to be odd. Does that make sense?
So their GCD must be 1.
Okay. If you look at the GCD of these two things, this and this is like an odd minus an odd, so this is even. And this thing is also an odd plus an odd, so it is also even. So 2 divides, like, 2 is a common factor, and we showed that um 2 is the only common factor. Like, there can't be a factor greater than 2. So the
But
GCD
2
is exactly 2.
2 can't be their GCD.
Oh, no, 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 wait. But t is odd, no? Like, if you have an odd number, like if you have like 3 minus 5 and 3 plus
Okay.
5, even, right? This is minus 2, this is 8, right?
Okay.
Hi, I lost connection. What have we done?
Oh, did you like, do you have this part? I just replaced A and B with perfect pth powers, and we
Okay,
got this, and I'm waiting. Like, I'm giving you some time to push this idea further.
okay. Wait, what's Mn to the L?
Um,
What is L there?
oh, A is equal to m to the power p.
No, what is L?
Oh, that's P. That's P.
Oh, where have I written L?
Mn to the P looks like an L. That's what
Oh,
I'm
oh,
saying.
oh,
Okay.
Oh,
yes.
I mean, you should remove B2 from the LHS, right?
Uh, Not yet, because okay, so when you're okay, I don't know the solution, that's why I'm not removing it. But when you're solving, you shouldn't just remove it if you're unsure. Like, okay, maybe when you come across, when you do the things and then you realize it's not required, then you can remove it in the actual write-up. But while solving it, it's not a good idea to remove it. In our case, it is required.
Like we could like subtract T plus P plus 1 by 2 and T minus P plus 1 by 2 to get P plus 1 by 2. P to the P plus 1 by 2
Oh,
in terms
acha,
of.
acha, do you want to remove T? Okay, yeah, 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 that we are going to do.
Yeah, that's what I'm saying.
Oh God, I have to type this again. 2 is equal to, I took it A, right? To the power P plus
2 to the
P,
power.
the entire V2 thing.
Mhm.
And to the power P. And that's right. You subtract, like, Okay, there is no point in adding because you don't know much about p. You want to subtract this one, like the first one from the second one, because then you get 2p to the power p plus 1 by 2 is equal to 2. If you take 2 common, then you have m to the power p minus 2 to the 1 minus 2 of n to the power.
Now to
Yes.
now use Fermat's theorem. Use
Okay.
mod p.
You want to use mod?
P.
Yeah, sure. Mod p. So 0 congruent to m, and this thing is just like minus 1 by 4 n. So m is congruent to n by 4. Oh, wait, sorry, we have a v2 by 4 times.
Hmm.
Wait, I don't get how you removed the V2. Okay, you're adding it back.
Yeah,
Okay.
make it a bit lower.
Okay, this looks bad.
That's right. What do you do? We have 8 minutes. So yeah, I'll give you maybe 2 or 3 minutes to push this further.
Can we say that m is congruent to n mod p?
M is congruent to n mod p. No, that is false.
But,
Like how can you conclude that from this?
but 2 and p are co-prime, no?
Uh, yeah. So no, but like you can't just cut it, right? Like if 2 was here, then you could cut, but there is no 2 here, so you can't cut. Is that clear?
Okay.
Yeah. You motivate frequency. We actually did quite a lot. We are on the third problem, right? Yeah, it's all right. Okay, it's 6:10. I think I should probably
Continue.
see
Yeah,
something
sure.
more. Yeah, I'll continue. Okay, so here's the idea. This is where this thing is like very useful. I'll just
I was trying to see if you could square it maybe, but it didn't look that nice.
We are not going to be squaring it, but yeah, we will use this condition because two things.
Okay,
We
did
know
we
that,
have this? Yeah, we just multiplied, right?
yeah, okay, two things. We have that m and n are less than p plus 1. So if we can identify what n is mod p, then m is just that value, right? If m is like, say, 3 mod p somehow magically, then m is just equal to 3 because m can't be p plus 3, right? So this is a very powerful condition. And the second thing is that, yeah, just multiply by m on both sides. So you get m squared.
Yeah, that's what I.
Yeah, you were right. Yeah, mn is congruent to p plus 1 about the thing. So p just becomes 0. So I'll just write 1 by 2 to the v2 of p plus 1. And we have a v2 of p plus 1 in the numerator as well. We had a 4 in the denominator. So m is congruent to plus or minus half mod p. Right. So this means that m is either equal to p plus 1 by 2 or p minus 1 by 2.
Okay.
Yeah.
Now,
And this basically finishes it.
yeah, this almost finishes. Like,
Uh,
m cannot be p minus 1 by 2 because m must obviously divide
The p plus 1.
p plus 1
oh,
by 2.
right.
Right. Yeah,
Mhm.
obviously, we want to make sure this p minus 1 by 2 is not 1. So we just say like p greater than 3 as well. Like we can check,
Sure, we can check the others. Okay, right. We have already checked.
yeah, we already checked a few cases. So yeah. So m is equal to p plus 1 by 2 and p plus 1 by 2 into n is equal to
So n is just 2.
v2. Yeah, exactly. Cuts, and then you have this thing, this thing. This is like at most 1 by 2, right?
Yeah, and that is
And
the
like,
case 1 by 2.
yeah, so for that,
So,
this v2 is equal to exactly 1,
yeah, so that also goes.
and n is also equal to exactly 1.
Yeah.
Okay, this.
See, that's why I told, like, I was saying that we should not throw out this v2 all at once.
Uh-huh.
Okay, so now just plug it into, where's the equation? Yeah. Okay, did I write this directly? Yeah. Now just plug it into the equation we had is equal to, wait, what do we have exactly? Yeah, m to the p minus 1. M we found out as this thing. By 2 to the p minus 1.
To the P
Yeah,
minus 2. No, yes. Yeah. Yeah, P minus 2. 2 to the P minus 2.
this, yeah.
Minus 2.
Minus,
2 to the P minus 2.
yes, that's right. 2 to the p minus 2. Like after the VP thing, this is important.
Yeah.
And this is just size. Well, actually, it's a bit tricky. Like, it's not direct. You have p plus 1 by 2 whole to the power p is equal to,
Yes.
right. So when you have this sort of equation where you know key size will be used, like the exponents are just different. You know size will be used. The bases are also different. So you just take like maybe p is equal to 5, see which side is bigger, and then try to prove that side in general. 5 versus 2 to the power 5 minus 2 is 3. 5 to the power 6 by 2 is also 3. So this is 3 to the power 5, 243, versus 125 plus 8 is 133. So this is bigger. So you would like, in general, this just becomes bigger, right? How do you prove it? Method number 1 is induction, just like I don't think it's very straightforward here, but like if you had maybe a general n instead of p, if you wanted to replace, then it would be more doable. But that sucks. So we will not do that. Method number 2 is just like bound somehow.
Wait, you're inducting on P, right?
No, we are not.
Then, like, how are you inducting? I'm not getting.
Oh, okay. If you want to induct, you replace p with a general variable n, and then show that this is true for large enough n,
Right.
and then just check.
Okay.
Right. That is what you would do. Here, okay, we want to bound this into a single term. Which term is bigger? Okay, obviously, like this term is much bigger. This is 8, this is 1
Yeah.
by 2.
P to the P plus 1.
You want to show that this thing is less than 2p to the p plus 1 by 2. Right. And see, like this is true. You know why? Because um, p plus 1 by 2 greater than 2 to the p minus 2 is the same thing as p to the p plus 1 greater than this thing squares 4 to the p minus 2. Use this 4 to the p minus 2. Yeah. You square both sides. And this is like obviously true.
Mm-hmm.
So you get this form. And now you want to see which is bigger. Right. So what you do is you take the pth root. So the pth root of the LHS is p plus 1 by 2. And we had a less than. RHS, if you take, we get 2 to the 1 by p into p to the p plus 1. Like, okay, p to the p by 2 times p ka square root. And you take like the denominator may p. So this thing cancels out. So you have p plus 1 by 2 less than 2 to the 1 by p times p
P is 1 over 2.
by
Yeah.
2p times square root of p. And you see why this is true, right? Like you have a linear, and as p becomes bigger, these things decrease.
Exponentially smaller. Yeah. So
Yeah, like and this thing just increases very slowly. So if it holds for like 1p, it will hold for all p more than that. And you can just see like p equal to 5 it holds. Like 5 plus 1 by 2, 3 versus is less than 2 to the 1/5 times, what is this? 5 to the 1/10 times square root of 5. Like, this is just obviously true. Like, obviously false. So we have a contradiction.
yeah.
As for the second case, we had two cases, right? Where did I even assume it? Yeah, here. Um, like the thing becomes ulta. So the veto of this thing is one and veto of this thing is the rest. We get, like, if you work it out, we get, oh my God. Yeah. We get the same thing, but like, the thing is flipped. So we will get p to the p plus 1 by 2 is equal to 2 to the p v2 of 1 and to the p. And
Right.
actually, like, I think variables will be split. Yeah.
Wait.
You do the exact same thing. You do the exact same thing to get that n is equal to p plus 1 by 2, m is equal to 1, the v2 of p plus 1 is equal to 1, and then you put it into the equation, and now the new equation you get is like p to the p plus 1 by 2. This is just like, uh,
1.
wait, yeah, you get
1.
it. Yeah. Yeah, this thing is just p plus 1 by 2 whole to the power p. You take it to the other side. Is equal to 2 to the p minus 2. And this is like an even easier condition because uh, this is just like greater than 2 to the power p. Like, I'll just write p plus 1 by 2 whole to the power p. And this thing is greater than 2 to the power p because p is
Yeah.
greater than 5. So that's a contradiction. And we are done.
This was a nice problem.
Yes, this is a very good problem. This is also quite instructive, especially in the part where you made use of this condition to turn the modular condition into something stricter, an actual equality. Yeah, like it's not used very commonly, but it is quite a powerful idea. And yes, that is the end of our class. If you have any feedback, you can obviously share. Um, I have one question which I did not discuss. I want to write it. Um, hold on, let me choose. Uh, yeah, okay. Uh, find all pairs of primes. Like this is like you should try this on your own. P, comma Q, such that 1 plus P to the Q minus Q to the P whole divided by P plus Q is also prime. The source is JBMO 2020. Actually, I'm not sure which year, but it is JBMO and it's a P4. I remember that. Yeah, it is. This is also a nice problem, but yeah, you should try this on your own. If you have any questions, you can stay. I'll switch off the recording now.